Hi, this is Mark and welcome to my video on my mini project for the course NMJ21404 Microprocessor Systems. For our mini project, we've designed a Morse code translator system based on the Intel 8085 microprocessor. The project is meant to act as a sort of letter-by-letter translator from alphanumerics to Morse code. The system is implemented in 8085 assembly language for the MY1SIM application. So for it to be used physically on the MTK85, delays have to be timed accordingly to the devices attached, used for us to be able to actually see what it displays. So let's start off with the basic setup of our system. First off, for the memory structure layout of the system, the default 8K ROM plus 8K RAM allocated in MY1SIM85 is used on top of an additional 8K RAM added to support our lookup tables used as well as placing the stack pointer further away from the program area of the system. This also helps to make sure that the stack area doesn't eat up important data inside our data area, or worse, collide with our program. It's important to note that the stack usage for this system is relatively small, otherwise we'd have to allocate more space to be safe. Next is the Intel 8255 Programmable Peripheral Interface, which we'll call PPIs from now on. 5 PPIs have been used for the system at base addresses of 80, 84, 88, 8C, and 90 respectively in hexadecimal notation. Now, thanks to the simulator software, we don't actually have to implement the decoding logic for selecting the PPIs. So all that's to do from our end is to determine the control words to be used. As for the IOs, we've used 3 keypads, 8 7-segment displays, 1 switch array, and 2 LED arrays, each bound to a specific port of a PPI, whether it be port A, port B, or port C. In our case, we decided to not separate the use of port C into the upper nibble and lower nibble, since the simulator mainly provides peripherals that come in 8 bits. For interrupts, we've declared the use of interrupt 6.5 and interrupt 5.5, which we'll discuss upon later. As for the mapping of the keypads, they are as shown on the screen. Without further ado, let's dive straight into our demonstration. So before we start our demonstration, let me load up our system. Right, so now once the system is loaded, you can click on simulate over here, which also automatically assembles our code if you have not done so. So next, we click on run. Now once we see the transmission LED moving, it means that our system is in idle mode and is ready to be used. So for the rightmost switch over here, it corresponds to the numeric keypad, while the second rightmost and the third rightmost correspond to the alphabet 1 and alphabet 2 respectively. So let's demonstrate first for the numeric keypad. So to select the numeric keypad, we click on this switch. Alright, so now we see that the transmission LED has stopped moving. So we click on 1. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and 0. So for the rest of the buttons, if you click on them, then they'll display nothing because there's nothing mapped onto it. Now next is the second numeric, the alphabet on keypad. So then after selecting the second switch, we click on interrupt 6.5 to reset our system. Alright, so once you see that there's nothing here, we are safe to click. So this is A, B, C, D. So to skip over to the next keypad, we have to select the third switch and click on interrupt again. So E, F, then G. Yeah, so we have to switch back to our second switch. So H, I, J, K, L, M, N, O, P, Q, R. So now we have to switch back. S, T, U, V, W, X, Y, and finally Z. So when we click on interrupt 5.5, and SOS message will be displayed and the system is set back. So if we keep the interrupt 5.5 on, the SOS message will keep on being displayed as well as the Morse code for it. So that's all for the demonstration part. Improvements upon the project could be done, including combining the three keypads into just one by using some extra logic to save up on the PPI usage. Next is to perhaps store the inputs into memory to be able to recall them as a sentence later on with a clear sentence subroutine perhaps. And also an inverse function of our original system, which is to convert Morse input, possibly via two buttons, into our alphanumerics. Now, admittedly, the use of LCD screens would have been nicer, but due to the application constraints, that will have to wait until whenever the author adds LCDs as an option. If the system was built for the MTK85, we could have scheduled our subtasks better to avoid polling, which is what was used for the system. In the next part, we'll discuss upon the nitty-gritties inside our code and how they are optimized to reduce the number of lines used. Thanks for watching.